So we have a little bit of unfinished business when it comes to differential equations. This is more of a conceptual idea. We didn't have enough time to talk about it before the exam. So suppose we have some differential equation of the form y prime equals a function of x and y. And we could try integrating this maybe, although this one, y prime equals x plus y, is not separable. Well, we can try other ways of approximating the solution. Now, if we knew that the solution did run through some point, let's say 1, 2, well, then my slope would have to be 3. If I knew that the solution to the differential equation ran through the coordinates 0, 4, well, then my y prime would have to be 4. I'm just following this equation right here. So I don't know exactly what coordinates the solution will pass through, to begin with. But I'm saying that if I did know they ran through some particular coordinate, I'd be able to calculate the slope because I have a formula for the slope. That's what the differential equation is. Okay, so does that actually help me? Can I visualize what's going on? Well, yes, actually. The trick is that we want to be able to think about all of these slopes at the same time, and that gets kind of hard. So we're going to use a tool, which is a different way of graphing information. So what we're going to do is we're going to record the slope the solution curve should have at a whole bunch of different x and y coordinates. And that'll look something like this. So some people call this a direction field. Some people call it a slope field. This is the very same thing. Some people call it a vector field. All this is doing is representing the slopes that a solution to the differential equation would have to have if they did pass through a certain point. And it's at each one of these points we've just drawn in a little line segment to indicate the slope the solution curve should have. And you can just kind of trace with your finger and follow the flow and see what the solution should look like, more or less. Now, if you're going to approximate a solution that way, it won't be exact. It's more of a heuristic. You can do this in a very precise manner, with computers, and ask a computer to trace through for you. Here in pink, we have the exact solution. And notice that when the pink curve is close to one of these blue lines, the slope of the pink curve is almost equal to those points, to the slopes of the blue line segments. Not exactly equal, but a good enough job to see that, yeah, this solution curve in pink is sort of following the flow as laid out by the differential equation. So this is a very useful tool when thinking about functions in terms of what's its slope? What slopes could it have? If my function started out somewhere else, my function started out down here, maybe it would bend in a different direction. but they all belong to the same family. All of those different solutions, they have different slopes, they have different places in the slope field, but in the end, they all belong to that same differential equation.